In this lecture of maxima and minima, we will discuss the behavior of f dash x at local maxima and local minima. Let us first consider the case when C is a point of local maxima for a function f of x. Observe that in this figure, the function fx is increasing for values of x slightly less than c. That is, in the left neighborhood of c, the function fx is increasing. However, at x equal to c, the function ceases to increase. Again, fx is decreasing for values of x slightly greater than c. That is, in the right neighborhood of c, the function is decreasing. Now that the function is increasing in the left neighborhood of c, let us assume that in the interval c minus h to c, where h is a small positive quantity, the function be increasing. And we know that when the function is increasing, the first derivative will take a positive sign. Therefore, we can say that since the function is increasing in the left neighborhood of c, f dash x is greater than 0 for x belonging to c minus h comma c. Similarly, we can say since the function is decreasing on the right neighborhood, that is in the interval c comma c plus h, f dash x will have a negative sign. That is, f dash x is less than 0. Hence, we can conclude that f dash x changes sign from positive to negative as x increases through c. Now, let us understand the same thing with the help of a proper graph. Here is the graph of a function f of x. Observe that the function here is increasing in the left neighborhood of c. As said earlier, we are considering the interval c minus h comma c, and we can clearly see the slope of the function here. This is having a positive sign. Now, the slope means the first derivative. Therefore, f dash x is greater than 0 in the left neighborhood of c. Again, we find that as the function is decreasing, the slope is showing a negative sign. That is, f dash x is less than 0. Therefore, f dash x is less than 0 for x belonging to c comma c plus h. And clearly, from these two, we can conclude that since fx is neither decreasing nor increasing at x equal to c, we can say that f dash c is equal to 0. Hence, whenever x equal to c is a point of local maxima, f dash x changes sign from positive to negative. Now, we will take up the case when c is a point of local minima. Again, observe this graph of any function fx. We see that f of x is decreasing for values of x slightly less than c. That is, in the left neighborhood of c, f of x is decreasing. And at x equal to c, f of x ceases to decrease. However, again fx is increasing for values of x slightly greater than c. That is, in the right neighborhood of c, fx is increasing. Therefore, since fx is decreasing in the left neighborhood of c, that is, in the interval c minus h to c, if we consider, we say that f dash x is less than 0. And in the right neighborhood of c, that is, in the interval c comma c plus h, we can say that f dash x is greater than 0 since f of x is increasing. Hence, we conclude that f dash x changes sign from negative to positive as x increases through c. Now let us see a better graph of the function f(x). Now here, as discussed earlier, observe that the slope of f(x) is having a negative sign in the left neighborhood of c since the function is decreasing. Therefore, f(x) is less than 0. And on the right neighborhood of c, the slope has a positive sign. That is, f(x) is greater than 0. And therefore, we can see that f(c) is equal to 0 when x equal to c, where the function is neither decreasing nor increasing. Now, in view of this discussion, we state the following theorem without proof, and this is known as the necessary condition for points of local maximum or local minimum. The theorem states, let f be a function defined on an open interval I. Suppose c belongs to I be any point. If f has a local maxima or a local minima at x equal to c, then either f(c) is equal to 0 or f is not differentiable at c. Now, as I said earlier, this theorem is only a necessary condition for the point x equal to a to be a point of local maxima or a local minima. However, the converse of this theorem is not true. Therefore, we have the following remark: a point at which the derivative vanishes need not be a point of local maxima or local minima. We will understand the same with the help of this example. Consider the graph of the function f of x is equal to x cube. Let us see what is the first derivative of this function. So, f(x) is equal to, therefore, 3x square. Now, let us evaluate f(x) at x equal to 0. So, we have f(0) is equal to 0. So, what do we observe here? The first derivative of the function is vanishing at x equal to 0. Does it mean x equal to 0 is a point of local maxima or minima? No, clearly this picture we can find that x equal to 0 is neither a point of local maxima nor a point of local minima. In fact, this point is called point of inflection. Now, let us see the second remark. A function may attain a maximum or minimum value at a point without being derivable thereat. So, again we will understand this with the help of this graph. Consider the function f of x is equal to absolute value of x. And here is the graph for this function. Clearly we can see the minimum value is at the origin, because the minimum value it can take will be x equal to 0. But however, this function is not derivable at x equal to 0. Now, let us interpret the theorem geometrically. So, geometrically, the theorem can be interpreted as the tangent to the curve y equal to f of x at a point where the ordinate is maximum or minimum is parallel to the x-axis. And this we have seen in the previous figures. So, if we see here, the tangent at x equal to c is parallel to the x-axis. Hence, we have discussed the behavior of f(x) at the points of local maxima and local minima.